All right. So today I want to do a little bit of work on friction and free body diagrams and doing the force equations when we add in friction. As we alluded to last time, there's a number of different little, whoops, sorry there. There's a number of different tricks that you kind of have to deal with. In particular, if you remember, there's three distinct cases for friction. There's when something is sliding relative to its surface. That's a pretty easy situation. There's something when it's about to slide or on the verge of slipping. That's also pretty easy. Both of those, there's an equation that we use for friction. Friction equals mu n. If it's about to slip, you grab one value of mu. If it's already slipping, you grab the other value of mu. But there's a whole class of problems where you can't really tell and you're thinking about it a lot. So I made some problems for you to help you understand that. So let me take a look here. Let's go into the workbook. Whoops, this one here. So on page, what is this here? On page 101, I'm going to leave these for you to do later. Normally I walk around the class and give you a chance to discuss these with me, but I want to point out something here on all this entire page. The idea here is I'm just trying to get you to practice which friction equation should you use? Should you use mu kinetic times the normal force, mu static times the normal force, or is it not legal to use either one of those, which is the third case there? Also, I'm trying to get you to think about the direction of friction. So to be honest, this entire page, we're going to do all these problems later, but this page here is not doing all those problems. It's simply thinking about friction in those problems. All right. And so you want to think about all the different possible frictional forces. I don't really want you to be drawing FBDs for every case because I know we're going to do all of these problems later. So I guess what I will say here is this page is to help you work on the directions of friction and which equations apply, if any. So don't spend a lot of time on these problems. I want you to look at it, think about it, take a guess, then read the solution. Some of these questions I deliberately left vague because I left it that way on purpose. So you'd be like, well, as worded, it's not clear. Sometimes that's the answer for some of this page. So don't beat yourself up on this page. Use this after class, go through them and think about it. Okay. And then that said, let's go on and start with this classic problem. We discussed this a little bit last time. So just to show you, we're gonna actually work through this problem now. This is 6.14, and I'll just show you that problem again with my book here. It's this problem, right? When I tilt this thing at some angle, when you tilt it enough, the calculator should slide. Wow, that's really on. Whoa, there it goes. So that's pretty exciting. One of the things that you'll see with friction is it's not always the same day after day, or even on the same day, trial after trial. The angle that makes the calculator slip, it tends to be approximately a certain angle, but it varies by 10 or 15 degrees sometimes, sometimes even more. All right, so let's take a look again at 6.14. I'm going to draw this up and you can draw it up. I'll bring it back up on the screen. There we go. All right. So 6.14. Let's rock this. Whoa. Okay. I should have some markers here. Oh, so 6.14. Okay, I got it. All right. And oh shoot, which way was it? I'm just going to check. Looks like I had the ramp going this way. Okay. So you've got a block here. In this particular case, what did we do? We raised a ramp until block on verge of slipping. So that's kind of the physical scenario that we're trying to describe here. In this case, which friction rule applies? In particular, I'll list them for you. Is it A, friction is less than mu static times n? Is it B, friction equals mu static times n? Or is it C, friction equals mu kinetic times n? It's about to slip. Which one of these should we use?
B?
Absolutely. So remember, when it's on the verge of slipping, that's when friction is the largest possible value, which happens to be this. I don't know if you remember, mu static generally is larger than mu kinetic. For example, this might be 0.3 and this might be 0.5. So this actually is the largest amount of friction right before it slips. Excellent. Nice job. Okay. So in this case, we're going to use friction equals mu static times n on the verge of slipping. That's what allows us to use that equation. All right. Now, what's something we do with every force problem?
Draw FBD diagram.
All right. So let's do that. Give me one force. What's one force acting on this block?
Friction.
All right. Which way is that going to point?
It's like the left. Like upward left.
Yeah. Remember, you could say down the plane, up the plane, perpendicular plane, up, down, left, right. So out of those, which is it?
Up the plane?
Yeah, exactly. So wouldn't the block tend to slide down in this case? So friction should oppose that tendency. Outstanding. And I'm going to use lowercase f for that. Somebody else, another force.
Gravity.
Gravity, which way is that?
Down the plane. Or it'd be like this. I don't even know how to describe it. Like this.
Straight up and down.
Yeah.
Just straight down. Now, we should be careful. There is a component down the plane, but there's also a component perpendicular to the plane.
Okay.
But usually we just say mg points straight down.
Oh, all right.
Nice. And you said that correctly with your hand, but yeah, and so it's easier to draw on a paper and yeah, but that's excellent. What else? Or is that it?
Who's normal force?
Yeah, which way is the normal force going to point?
Perpendicular to the ramp.
Yep. Now, usually, not always, there's weird exceptions to everything, but usually we're going to expect the normal force to be larger than the frictional force. Now, what's the acceleration of this thing? What do you think? And what's your reasoning? Well, let's just start. What do we think the acceleration is? Something or nothing?
0.
Why do you think it's 0?
Because it's on the verge of slipping. Which
On
means
the
it's not moving.
verge of slipping. Yeah, it's not slipping yet. So I guess you could choose any coordinate. I don't know why. I just chose this way. Maybe because it fit on my paper. You can see I was running out of board. So you could do this any way you want. You could call this way positive. You could call that way. I don't know. I guess what I'm thinking in my mind is if it did start to slip, I'm going to call that the positive direction. Because if it did start to slip, then X and acceleration would point the same way. That's what I think went through my mind, but I don't know. All right. Now, strictly speaking, this is not an FBD, right? Because we still have the ramp in there, which could be kind of convenient, actually. Take a look. This angle's theta. What's this angle that I just made 2 dots here? What's this angle?
90 minus theta.
90 minus. Excellent. So then typically when I'm splitting this thing up, I need to split up this mg vector, what's this angle that I'm trying to point to?
Angle theta.
Theta, money. And in this case, I'm calling it theta critical or theta subscript C. This is the one special angle that puts this thing on the verge of slipping. Like I said, in practice, it's usually a range of angles, but this is the predicted theoretical angle at which it should slip. All right, so I'm going to split up mg. Is that looking good? For splitting it up?
We need the cosine and the sine.
Yeah, so is this looking, so would this be a sine or a cosine, or is this wrong?
That's not good because it's not parallel to the
Yeah,
slope.
I'm just trying to do that over and over again just because that's the common one. Remember, your components need to be here. And now notice the components are smaller than the vector itself. Had I gone all the way down to here, this side would have been larger than the vector itself. That's not a good basis set. All right. So somebody said mg sine and cosine. Hopefully you see that this is mg sine opposite and this is mg cos. I'll label this one because there's room, maybe. Actually, there's not. Let me write it like this. And then the other one would be mg sine. All right, so let's go ahead and write our force equations in the x direction. Somebody give me a force, plus, minus, whatever. What do you think? Are there any positive forces in the x direction?
So it'd be mg sine theta.
This one, yes. This is going down the plane, and that matches that. So that's beautiful. mg sine, in this case, of theta subscript critical. All right. Anything else in the x direction? Someone else?
Negative friction.
Negative friction. And then all this is equal to, there's no more in the x direction, agreed? This one and this one are the only ones in the x. So this should all equal what?
0.
Yep, because it's mass times acceleration, which is 0. Excellent. Nice job. All right. Let's go on to the y direction. Okay, somebody give me a force here. What do you think?
Would it be your normal force?
Okay. Positive or negative in this case?
Positive.
Normal force is positive. What else we got?
Negative mg sine. I mean cosine.
Yep. And that's it. So this is all equal to mass times, I guess I should be careful here. I'll call this AX and I'll call this AY, but they're both 0, right? So that's cool. All right. Now, generally speaking, here's a cool trick. There's an equation we've written that we haven't really used. It's right here. F equals mu n, and it's so blurry, I'm going to rewrite it down here now. Or actually, I could squeeze it in if I do it like this. On the verge of slipping, we could use this. So a classic thing that people would do at this moment is you could say, if this equation is legal, shouldn't I figure out the normal force here, plug that into there, and then shove this in for F? And that's a general strategy that is very useful. Again, a lot of times with force problems like this with friction, what you do is you write the force equations. If you have a friction equation like this that involves the normal force, immediately solve for the normal force in one of your equations if possible. shove that into here, and plug that in. I'm going to do that right now. So tell me here, I think this one's not too bad. This just says N equals mg cosine theta critical. Now, if I plug that in, it says that friction is equal to mu subscript S. Why? Because it's static. It's on the verge of slipping. Mg cosine theta critical, which now I'm going to plug that into here and something magical happens. Watch this. Whoops. I'll pause for a sec. What's something that every term has in it that can be factored out and eliminated in this equation?
mg.
Oh, so notice not only does the mass not matter, the planet you're on doesn't matter either. G changes as you go to the moon or to Jupiter or something, right? So that's kind of crazy. Now, said another way, look what I'm going to do here. I'm going to take everything. I want to divide this term by mg. So that means I have to do it to every term. And because you have 0 on this side, it's not going to matter. Whoops, let me lower that down a little bit. So again, if I do something to one term in the equation, multiply by 3 or divide by 7, I have to do the same to every term. So when I do this, the mg's drop out. Well, 0 is still 0. And so from this, I'm just going to rewrite this equation like this. Moving this to the other side. We get that. Now, believe it or not, I have no idea what we're trying to solve here. So I'm going to actually read the question now, and maybe I'll bring that back up. So all I was doing at this point was I drew an FBD and I wrote down the force equations. And because we had this extra friction equation, I used it. I still have not looked at what we're trying to do yet. And this is basically the habit I want you to get into. Draw a picture, draw the force equations, read. At this point, we've kind of cleaned up this. I have a feeling we're looking for mu static because we know theta critical. That's the only unknown. But let's take a look. I'll screen share and see what we're supposed to be doing here. Whoops, wrong one. Let me get this out of here, Zoom. This one here. Okay. Which friction case? We discussed that. Sketch the FBD and force equations. We did that. Okay, so part C, notice it says solve for the appropriate coefficient of friction. So we are supposed to get mu static there. All right. And so maybe just to make this clean, let's bring this into here. What question is this? 14. All right. So notice when you work this around, we get, I guess I could just show you. I got it on the board here. The idea here is if you divide by cosine, sine divided by cosine is tangent. So let's go ahead and just work that out really quick. So solving for this, cosines cancel here. This is equal to tangent theta critical. And so this is a classic way to figure out the coefficient of friction. You may be wondering, how do people figure this stuff out, right? Well, here's an example. You take this book and you turn this thing very slowly. And at some point, maybe, wow, look at that thing. Look at that. Look at that angle. What angle does that look like? Eyeball it.
75 to 80.
Isn't
Yeah, I was
that
about to say.
crazy? This should not be happening, but it does. And this is one of the things that's annoying about friction. We teach you lots of things. We teach you lots of things in classes, and we say, oh, coefficients of friction should never exceed the value 1. Let's try punching in the angle that we just found. Let's just say it was 60 degrees, right? It was clearly more than 45 degrees, but let's just punch that in. So if I want to get the coefficient of friction for this, I'm going to do, I knew class would be a lot more fun. Let's just say a tangent of about 60 degrees, right? It says the coefficient of friction is like 1.7. Now, these coefficients are supposed to be less than that. It turns out in the real world, this is only an approximation. If you had something like a cardboard box sitting on a ramp and you had, say, 700 of them, most of them would end up having a coefficient of friction pretty close to the same value. But every once in a while, one will give you this really bizarre situation. And so we were probably getting some light chemical bonds forming. And now if I could show you this, I don't know if you could see this very well. See this little pad here, right? So this is some kind of squishy rubber. And so maybe, I don't know if you can tell that, there's a couple of those on there. There's 4 of these little pads. So it's not just like a plastic surface sitting on a book, because that would slide easily. And I could show you that by putting these. Now remember, these are not rubbery buttons. These are plasticky buttons. So what if I did the same experiment here, but with these plasticky buttons? It's going to start sliding right away, right? So in certain weird cases, and rubber is one of these weird cases, you could get some weird stuff going on. And I've actually seen what we just saw many times in lecture. I use hockey pucks, and I'll have people put these hockey pucks on there. And depending on how hard you place them or how recently they've been cleaned, or if there's, all kinds of weird things can happen. Maybe there's weird irregularities in the surface slightly in the book. So maybe it's getting, all kinds of weird stuff can happen. So that said, take all this frictional force being mu static times the normal force with a grain of salt. It's a good model to get started and make predictions. Then when you want to actually build something or do something, you better test it many times and check it. All right, questions about that? That's how you can get coefficients of friction or get an estimate for them. All right. I'm just going to show you this one last time. I'm going to do the same experiment and just show you. I have a feeling if I do the same experiment, whoops, let's get this right. It'll probably be a much different angle. Oh no, it's still holding on there pretty good. This is the craziest thing ever. Look at that. Wow. What? That's even steeper. That's crazy. Oh my gosh. Here's another thing you could do, like take a mouse pad or something like this. I don't know. Sorry, I'm actually having fun with this, right? Oh my gosh, that's crazy. Anyways, whatever. You could do this around your house and test things and get out a photo and take a picture and then try and measure the angle with a protractor or something. All right. Anyways. All right. That's great. Questions about the actual problem? Any questions about the problem or the physics of that? All right, let's move on to the next one now, okay? Or let's see if there's anything I forgot to solve. All right. Oh, okay. Let's look at this one. If I had used a block with twice the mass, according to the theory, how is the critical angle affected? What do you think?
It'd be the exact same.
Exactly. And so this is something you could test in the lab. And again, I don't know if you noticed, there's a lot of statistical variation here, but if you do this hundreds of times on average, we'll see that the mass doesn't matter. Okay. Yeah, good. Let's see what else we got in here. All right. If we use an angle above the critical angle, can we use friction equals mu n? Yes or no? And if so, which coefficient? What do you think, somebody? If we use an angle bigger than theta c, what happens?
It slips, right?
Yeah, so could we use F equals mu n?
Yeah.
Which coefficient would we use?
The K.
Absolutely. Perfect. Don't overthink it. You got it right. What if we're below the critical angle? Somebody else. If you're below the critical angle, is this thing going to slip? So if you used a smaller angle,
No.
it wouldn't slip. So could we use this equation?
Yes.
No.
No.
You can only use this equation with the mu. So remember, it's tempting to say, why don't we just use mu static times the normal force? But remember, this is only valid on the verge. So if it's on the verge of slipping, that's true. If we use an angle that's lower, it's not on the verge of slipping anymore. It was only on the verge of slipping at this angle. Did that make sense, Erica?
Yes, it did.
Yeah, so this is where it's tricky. We just did a problem where we used, so at the angle it's about to slip. So if it's just about to slide, then we use F equals mu static times N. If it's above that angle and it is sliding, friction equals mu kinetic N. And if it's below, oops, I hit the wrong button. If it's below, look, right here, F is equal to mg sine theta critical. Oh, I mean, sorry, if we're at a lower angle, F would equal mg sine theta. So in general, anytime it's about to slip or if it's not slipping, this relationship is true because it's not accelerating. And I'd say that this vector has to balance this vector component. So we'd say the F has to equal mg sine theta so that it doesn't accelerate. So in general, that's true. If it's on the verge of slipping, this extra piece of information is also true. Is that helping?
Yeah.
Maybe. All right, cool. Cool. All right. Let's go on here. This one, I'm going to let you try this one on your own at home. But so it's very similar, except now the block slides. So as we just discussed, it's very similar, only now, is it going to be accelerating? Yes or no? What do you think?
Yes.
Yes. And so now we can't set A equal to 0, but we can use F equals mu kinetic times the normal. So it should look nearly identical to the last problem, except A is not 0 and you have to do a little bit of work. Also, friction is not mu static anymore. It's mu kinetic times the normal force. All right, so you could use kinematics, blah, blah, blah. All right, let's try this one right here, 6.16. Let's see what we could do with this, all right? I'm going to let you read this for a second, and I'm going to get my whiteboard cleaned up. If there's any questions, unmute anytime, ask the chat. You could ask Jay, ask me, you know, let's get this party going here. Six point 16. Ramp's going the other way. Okay. So we've got mass 1. So I'm just going to make a quick list of my givens here, just so I can keep track of the things that are given. Looks like mass M1 is given. M2 is given. H is given. Mu static and mu kinetic. And then theta is given in the picture. So I'm going to assume theta is given as well. All right. And then I guess it seems reasonable to assume this is happening on Earth. So even though it's not specifically mentioned, I am going to assume G is given as well. So again, I'm assuming here that the masses were given in the problem statement, theta was given in the figure, H and these were given somewhere in the statement. And unless otherwise specified, usually we assume we're doing problems on Earth and G is a given. All right. There we go. Get rid of that light. All right. So in this case, that's what I started with. Again, I'm just listing these so I don't have to keep looking for them. That's sometimes useful. All right, let's go back and see what we're supposed to do. Okay, what conditions apply? Okay, if we want the tension to be equal, does anybody remember? Obviously, you could look it up, but
If tensions are equal, is acceleration 0?
no. You
Okay.
could have the same tension and still be accelerating. That's a good guess. Not it.
If it is the pulley axles negligible?
Yeah,
friction?
negligible axial friction and there's low friction on the axle and then low mass. If the pulley is massless relative to the blocks, which it usually is, and as long as there's not a ton of axial friction, that's what helps us say this stuff. All right. What about this? What condition, if the acceleration magnitude of each block is equal, what does that tell us? Or what condition has to apply? Does anybody remember?
Does that mean the cord is inextensible and frictionless?
Inextensible, yeah. Turns out the cord can have friction, so that's not a. If there's going to be some friction right here, and there actually has to be, otherwise it wouldn't. Well, actually, it could slide over the pulley too, but yeah. Generally, we say it's inextensible, and remember that means non-stretchy. So the non-stretchy string. Basically, don't use bungee cord. Got it? Okay, got it. I'll put string there just so we got it. And then the next one. What does that say? If the acceleration is constant, what's the last piece? Do you remember? Had something to do with the string. I'll give it to you so we can get on with this. Massless. Now, obviously, no string is really massless, but compared to everything else, so sometimes we'll just say a very light string. So we're using a light string that doesn't stretch, and we're going to use a pulley that is very light and has negligible axial friction. So that takes care of these first three bullets. All right, so unless otherwise specified, we always assume those to be true. Otherwise, it's too hard to do the problems at this stage. We can handle that later in a later class. All right. So what do you think? Let's look at part D. How should the tension in the string compare to M2G? What do you think?
Equal in magnitude, but negative in direction.
Nope. Not necessarily, I should say. It's very unlikely that's true. We're told in this problem, M2 moves towards the Earth, right? If it's accelerating downwards, which is most likely, is M2G equal to tension?
No.
No, which one would be bigger?
M2G.
Yeah, so we're expecting this is bigger. Now, it is possible it would slide at constant rate. We aren't exactly told that. However, the odds of the frictional force exactly balancing this at some random angle are almost zero. So I guess I'm making another assumption. I'm assuming it accelerates. Now, part of the wording of the question gives us that clue. It says what must be true for the acceleration. So we're assuming some acceleration here because the question asks about acceleration. I agree. It could probably be more clear, and I could literally state whether it's accelerated or not. And usually on exam questions, I do that. But sometimes I deliberately leave these vague, so we have to kind of talk and think a little. But I forget who it was that said T was equal to mg. That's possible if it's not moving or if it's moving at constant speed. But based on the wording of this question, I don't think that's true. Does that make sense why I'm saying that now, whoever that was? Hopefully. So it's sneaky. Yeah, the most common mistake here is people assume these are always equal, and they are sometimes equal, but not always. I think this is the case. So let's go ahead, draw the FBDs. I'll do it as well, and then we'll compare. I guess I've already done one of the FBDs for you. So I kind of already did this one up there. But notice I just made the assumption that I might as well rotate this coordinate system to follow that. Might as well align the coordinate system with the acceleration. What's one force acting on mass one here?
Tension.
Okay, which way is that? Up, down, up the plane, down the plane, left, right?
Up the plane.
Up the plane, good. Okay. What else we've got on it? Somebody else.
No more force, parallel left.
Okay. So I'm going to assume you meant parallel to this y-axis. Sorry. So again, it goes perpendicular to the plane, which is parallel to that axis. I think that's what he was meaning. Is that right? Or I don't know. Was that Gage?
Yeah, sorry.
Okay, gotcha. Then what else? Somebody else.
Gravity,
Okay. Which way does that point?
straight down.
Nice. How would you label that?
M1G.
Nice. Nice job remembering that subscript. Okay, so we're all done, right?
Oh, we forgot friction.
Very well done. Which way is friction in this case?
It's going down the plane.
Yep. So we see it's always careful. We got to think about friction a lot. So hopefully this is kind of good there. Now, which of these vectors need to be split up to match the components here? It's kind of hard drawn from the side, but
M1G.
yeah. So in this case, we know this is straight down. This one needs to be split up. The rest all fit on the coordinates. So take a look, just without doing all the 90 crap. Is theta a big angle or a small angle in this figure? By big or small, I mean compared to 45 degrees.
Small.
Small. So which one is this, theta or 90 minus?
Theta.
Theta, because it's also the small one. Now that's a trick that you could use, which works for these inclined plane to save you some effort. So that's supposed to be a theta right there. Isn't that a Greek fraternity, Iota Theta? It was tasty too. All right, so this side's going to be mg. Whoops, no, it's not. It's going to be m1g. Sine or cosine? Cosine. Adjacent. Okay, and so notice here we go. In this case, can we use any of the special equations for friction? Specifically, does friction equal mu static times the normal force? Is it something less than that? Or can I use mu kinetic times the normal force? What do you think?
Mu kinetic.
Exactly. Why? What's the reasoning?
Because 2 is already accelerating towards the Earth.
Exactly. So is one sliding relative to the surface?
Yeah.
Yes. So as long as one is actually moving relative to what it's sitting on, mu kinetic applies. So we could use friction equal, let's do that in green here. Friction equals mu kinetic times the normal force. So now we could write the equations, stack them, and add them and learn something. I don't know what we're supposed to learn, but let's go read the question. Okay. I think you could write down the force equation. Okay, so we're trying to find the impact speed of M2. Any ideas? So I think you could write the force equations. We know we have the block here. Let's assume you could get that done. How would you approach getting the speed of M2?
Would it be trying to derive that equation from earlier? The like ms equals tangent?
That's okay. I'm not sure what you mean there. So let's go look at what I've got written here. Maybe let's just start here. Let's actually get the force equations because that's part of what you're describing, right? So
Yeah.
let's at least do that step. Go ahead and write down the force equations, what you think they are. Okay. And then when you get a chance, I do have the solution up on screen, but go ahead and try and write it without looking at the screen first. And let's take a look at these now. I have no idea if I'm giving you enough time, but I probably should wait. Oh, wait a minute. 30 seconds. Okay. So hopefully that's about enough time. So there's our equations. Was that Gage you were suggesting an approach on, right? Our goal was to figure out in the next part get impact speed. What variable is that? What is impact speed?
Velocity?
Yeah. Velocity initial or velocity final?
Final?
Any ideas how you would approach this?
Let's see. You could do acceleration. Acceleration is equal to change in velocity or change in distance. And then you can solve for V.
Careful. You said acceleration is equal to what?
Change in velocity over change in distance. Oh, yeah, change in distance.
And that's not right. What are the units on this side?
Meters per second squared.
What are the units of velocity?
Meters per second.
So what needs to be on the basement here?
Oh, time. Oh, change of time. Yes, change of time. change of
You've just
time.
misspoke. Nice job catching it though. So that's when the unit check actually pays off because everybody does that once in a while. Where you're like, oh, whoops, I just misspoke, right?
Yeah, I don't know
So
why I did that.
yeah, that's all right. Now you could use that. Okay, and we're getting on the right idea. What else could you use that relates acceleration to velocity?
One of the original 3 equations from the kinetic. Chapter.
Kinematics, 1D constant accel, because acceleration is constant, right? Because the string is massless. 1D constant accel kinematics. And so we know that V final squared equals V initial squared plus 2 times, I'm going to make a mistake here, GH. Why is this not right? I thought the acceleration was G. It's not. It's falling down.
It's negative G?
Nope.
Because it's not in free fall.
It's not in free fall. There's a string attached to it. Right? So this does not work. We can't just say that. It's A to A delta Y. Now I want to point out here, if we point our coordinate system this way, delta Y, is it going to be positive H or negative H according to this coordinate system?
Positive.
Positive. And then the acceleration in the Y direction would be, I guess we could call it delta X, shouldn't we? I guess I should label those. Doesn't really matter. Let's clear this out. But I just want to point out, if we call this the X direction, then this distance here would be delta X. So strictly speaking, delta X would be positive H. We're told in the problem it follows distance H. And A sub X would be positive A. Well, how can I get the acceleration? Any ideas? These equations. Now, here's where we run into trouble. Masses are known. Acceleration is unknown. We need that. If we could just get that. Oh, by the way, we're also told V initial was equal to 0, right? Wasn't it released from rest? Okay, we know the angle, we know G, we know M1, but I don't know tension, and I don't know the frictional force. Shoot. I don't know the normal force, but I do know this, this, and this. So I could get the normal force. Over here, I don't know the tension, and I don't know. What would you guys do here? Tell me. I'll put dots to indicate the stuff we know.
Would we combine forces to cancel out certain forces? Like we
What
did in
do
the
you
last
mean?
chapter? Like we did in the last chapter, like where we add like the forces of X together?
Add this and this. Okay, if
Yeah.
you do that, which force gets eliminated?
Tension.
Tension gets eliminated. Excellent. But we still have this one. How do we get rid of that?
Do we add the Y forces together too?
Well, nope. This one doesn't have any Y forces.
Hmm.
Other thoughts?
Well, we could solve for t using the x for the FBD2 and then plug that into the x for the FBD1.
Okay, but then you'd still have this unknown right here. That's a good strategy. That would also work, but it's the same thing as what we just discussed in effect, and we still have that unknown. How do we get rid of that friction unknown?
Does that have to do with one of those like F equals?
Aha!
forces?
What do you mean? Which friction case applies?
Mu kinetic.
Mu kinetic times the normal. Well, wait a minute. Can't we get the normal force here? That we could figure out. Aha! I could use the normal force, figure out this. Then I got this. Then I can get this. Then I don't have any unknowns. Then I can get the acceleration. Then I can do kinematics. This is a typical physics problem in that it seems impossible unless you remember to do all the setup. So let's go to our picture here on the right. Actually, let's just do this. So if I scroll down, I could use this. And if I solve this for the normal force and shove it in, the frictional force is no longer unknown. And now it is exactly the same as before. You take this equation right here, you stack it and add it with this equation. Tension, the internal force drops out, just like this right here. And notice, you know, you don't have to do it the way I do it, but why do I do it this way? I end up with M total A on the right. No internal forces on the left. This helps me check if I made a mistake with the plus or minus sign in my FBD or the force equations. So just pausing here, can I just divide everything by mass and have it drop out? What do you think?
No, because there are different masses.
Exactly. There's different masses. And so once you have two blocks, usually you're left with just big, ugly messes with subscripts here, blah, blah, blah. Okay, that's fine. And so you get something big and ugly. We plug it into kinematics and it's even bigger and uglier, but so what? All right. And so I think you guys did pretty well on that. All right. I'm going to pause for a second. Does anybody have any questions while that's up there that I can help? What do you think? It's basically exactly the same as chapter 5 with one extra step. This. You got to think about friction. Oops, let's get the chat there. Oh, no. It will get easier. I don't know. So this is now full speed. This is a real physics problem. This is not some toy physics 110 problem. This is like you're almost ready to be in a, engineering physics class. You should be almost doing real problems. This is pretty close to one, right? This is a decent problem. it's practical. You could imagine having a system where a block is being pulled over a pulley. This is a reasonable physical scenario. And there's, yeah. So again, Angel, was there something in particular that was tough for you about it that we could discuss, or what are you thinking?
Oh no, it just kind of messed me up how we're supposed to use equations from like everything we've learned so far.
Yeah, right. Yeah, this is another thing about physics, right? You never get a break. Is that true, Jay? Jay's still in Jay. Have we used kinematics in Physics 163?
Yes.
Have we used all of this in 163 at some point?
Yes.
And didn't we have a problem just the other day where I screwed with your class with this same problem?
Yes.
And didn't everybody miss it? Yes.
Everyone missed it.
And you just want to cry as an instructor, but whatever. We'll blame it on online teaching. That's it. That's it. So it's not easy to remember. Now, give yourselves some latitude here. Remember, you have been raised from birth to think about things as you see them. And people all over the world, especially in the movies, are feeding you all kinds of lies visually about physics, right? Superhero movies don't make any sense. Nothing makes much. And then the fact that there's always friction in the real world is complicating. And we see just how complicated friction is. And people have a tendency to associate motion with acceleration, which is also wrong. Motion and acceleration are not, it's not good to think of acceleration as straight up motion, right? It's one type of motion. So accelerated motion is one subset. Motion could be moving with constant speed too, constant velocity. Anyways, all right. So yeah, pretty excited. I don't know, other questions out there. Imagine when you have to plug in numbers and get the sig figs right too, right? And then the units and the after your final exam. I hope you guys do all right on your final. It's gonna be fun. We'll see. We'll see. It's all the stuff we've been doing, but yeah, I have no idea with the online teaching how it's going to affect you. Yeah. Just don't worry, it's not nearly as hard as Jay's final. You're screwed, Jay. You're so toast. Your guys you'll be all right. But it's no joke. Yeah. All right. You'll be fine if you've been practicing. Let's get back to work here. Yeah, you'll probably be fine, Jay. You'll probably end up getting an A. All right. Let's go back to here. Let's see if there's anything else. Ooh, this is a good question here. All right. So let's try to refocus here. Okay. So let's think here. When I say what is the minimum M2 required to cause M1 to slide upwards? When you see this question, what are you thinking? Just kind of walk me through what's going on in your brain so I can try to help.
It kind of makes me want to think that M2 should be heavier than M1. So that it goes, so it causes the block to kind of like slide up.
It turns out that's not always true. It depends on the angle a little bit. Think about this. What if your angle was very slight, like 2 degrees or something like this, right? And let's say block 1 was 10 pounds. You might be able to make it slide with a 1 pound block if the friction's low enough, right? So just be careful with that. But yeah, so that's not quite right. Can you think of a way to modify it? He thinks that, yeah, okay, that's true. Good thought. Not quite always true. It might be true in some cases. Other ideas?
It's going to be on the verge of slipping.
Aha. If it's on the verge of slipping, does our old math still work out?
No.
So start over. FBD. A new FBD. And then you said on the verge of slipping. If it's on the verge of slipping, does our old friction equation still work, or do we need a different one?
Different one.
What is that new one?
F equals mu Sn.
That's right. And so basically you start all over, but you do get one benefit. If it's on the verge of slipping in this case, what else does that tell you?
That mu is equal to the tangent of theta.
That was
Acceleration
true
is
when
equal
there
to
was,
0.
yeah, I was going with this. Acceleration is equal to 0. We do not know that mu static is tan theta critical. So just because there's an angle here doesn't mean this happens to be the critical angle. The critical angle, that was a good thought. But if I scroll up here, it's a very different problem because this one didn't have a rope on it. So the critical angle only works for these problems where there's a block on a ramp and you change the angle. That's it. This one is different because there's a block on a ramp with an angle, but there's also tension. And this gets extremely tricky. Think about it. If 2 is really large, it's going to go this way. And then there's going to be, this one would tend to move up this way, and friction would point down the plane. That's terrible. Undo. Right? So sometimes friction would point down the plane. However, what if 1 was really heavy? If 1 was really heavy, you could have acceleration this way, and then you could have friction up the plane, right? So it's not obvious whether we need to do this or that. There's a large number of cases here, as we discussed last time. You might use this lowercase, you might use the uppercase. So again, sometimes this thing might accelerate up the plane, sometimes it might accelerate down the plane, sometimes acceleration could be 0, right? So depending on the values you use for 1 and 2, this could be tricky. So when I read this one, it says what minimum M2 is required to cause. That's what tells me, okay, this is this situation. A goes to 0. And then this goes to mu static n because it's the minimum amount, right? It's on the verge of slipping. All right. I'm going to pause on that. I don't know. Questions about that? Let's go look here. This is what I said in the solutions. If it says the minimum mass, we're on the verge of slipping, we could still use that, except we got to switch it to mu static. And it says A is not equal to 0, or A is equal to 0 in this case. And then I ended up with this result. All right. All right. Let's see what else we've got here. Let's try and squeeze in one more. Ooh. Yeesh. Oh, mean old Mr. Jorstad. Okay, if this gives you trouble, try 6.18 and a half first. Well, it's probably going to give us trouble since we're getting started here. So maybe we should look at 6.18 and a half. All right. Oh yeah, these problems. Oh my gosh. All right. So I'm going to let you guys try whatever you want, and I'll let you work on either 16.18 and a half if you're having some trouble, or 16.17 if you're feeling like you're kind of getting this. So I want you guys to try out one of these two problems, and let's see how many people we got here. I'm going to set up some breakout rooms, and you could just finish the day working on one of those two problems, whatever you want. Okay. So we'll go 2 rooms. We'll just put people in there randomly here. All right. And so go ahead and join those up and try working on a problem there. And if you want, I'm going to go ahead and stop the live stream now. You've got the solutions. You've got Jay, you've got me. Jay, I'll go into the breakout room you don't go into. All right. All right. Go for it and go ahead and finish out strong for the next.